Alright, so good news and bad news about this section. The good news is that there's really only one thing to learn in this section. And it's going to be what we call this partial fractions formula, or this method of breaking something up into partial fractions. However, once we learn how to do that, integrating after that is going to be a bunch of stuff that we've already integrated before. Right? So, like, for example, if we take something like this and I ask you to integrate it, that should be a rather simple integral problem compared to a lot of the stuff that we've been doing. One thing that's going to come up a lot in these integration by partial fractions is, power rule, u sub, ln, and then this little guy right here. Let me make that a little bit better. So this is a formula that certainly deserves the respect of a flashcard, and it's going to be super useful for us in some of these integration by partial fractions problems. Now, for the most part, what we're going to do is we're just going to focus on getting this partial fractions method down. And then after that, I'm not really going to integrate. I'll talk about like what we need to do to integrate after that and set up the integral, but I won't actually solve for the answer. I'm expecting that y'all will, go through it, solve for the answer. You can double check it with an online helper. If something looks weird, you're free to bring it to me at any time. But like I said, a lot of the stuff we're going to be integrating looks like this. And so it's stuff that I'm really confident y'all can integrate. So let's talk about this partial fractions formula. Oh, first let me get to the bad thing. The bad thing about this section is that it is super, super, super important that your algebra is reliable. Meaning just simple stuff such as adding and multiplying, and even just making sure we're distributing stuff correctly and carrying our numbers down correctly. That sort of stuff is going to be extremely crucial, and it is just so easy to make a mistake. So I think that's probably the hardest part of this section. So let's go ahead and get started. This method of partial fractions is going to be used to integrate what we call rational functions. What I mean is a rational function is something r of x that is written as p of x over q of x, where p of x and q of x are polynomials. Now, in order to use the partial fractions method, we need the degree of p of x, our numerator, to be less than the degree of the denominator. Right, so what I'm saying is that something like this is not okay, because the degree of our numerator is 3, and the degree of the denominator is 1. When we get in a situation where p of x has a greater degree, then we're going to use long division to divide q of x into p of x, so that we can write something that looks like this. Right, so this looks really weird right now, and I've already written out the answer, but let me give a quick reminder of how to do long division on polynomials, because it's probably been a while for most of us. So what we'll do is we take the denominator, we stick it outside, take the numerator, stick it inside what I think like some people call the house or whatever. And then what I'm looking for is, what do I need to multiply x by to get x cubed? Well, I need to multiply it by x squared. And so now what I'm going to do is I'm going to multiply x minus 1 by x squared. When I do that, I'll get x cubed minus x squared. Now what I'm going to do is flip the signs on everything that I've written in this row. So this is a positive x cubed, we'll make it into a negative x cubed. This is a negative x squared, we'll make it into a positive x squared. Now we can go ahead and add these two rows right here together. So we'll get x cubed minus x cubed gives us 0. X squared plus, there's no x squareds up here. So this is just going to be plus x squared. Oops. So plus x squared plus x. Now, what I'm going to do is the same thing again. I'm going to say, what do I need to multiply x by to get, now I look at this new row. And I'm going to look at the thing with the highest degree. So what do I need to multiply x by to get x squared? Well, I need to multiply it by x. So I do plus x. Now I multiply x minus 1 by x. So that'll give me x squared minus x. Flip the signs. And so now we'll get 0 plus 2x. And so now I do this one more time. And I say, what do I need to multiply x by to get 2x? Well, I need to multiply it by 2. So I do plus 2. And so I'll have 2x minus 2. Flip our signs. And we'll be left with the remainder of 2. Right? So way back in like first or second grade, we would write this as R2. So then what we say is we say that x cubed plus x over x minus 1 is equal to, I'm going to take what I have up top, which is the x squared plus x plus 2. So x squared plus x plus 2. And then I'm going to do plus whatever my remainder is. So I have a remainder of 2 divided by whatever we were dividing by, right? Divided by the denominator that we had at the beginning. So plus 2 over x minus 1. And so that means that we would now be, instead of trying to integrate something like this, right? We can't use u sub here. I don't see any trig identities that we can use. It just looks like something that's going to be really difficult to work with. So instead, what we can do is, instead of integrating that, we integrate something like this, right? Where we use power rule, constant rule, power rule, whatever you want to call that. And then ln rule with the u sub right here. Okay? So that's the goal of partial fractions, is to be able to integrate something like this. So that was one of our cases of like, how do we do long division to set up a partial fractions problem. This right here is something that's nice to integrate. A lot of times when we do long division, we're not going to have a nice remainder, or we won't have a nice denominator. So a lot of times what we'll have to do is we'll have to do partial fractions on this. Remember, this is just long division. We haven't actually done the partial fractions method yet. But now what I've done is I've gotten something where our degree up top, this has a degree of 0. This has a degree of 1. So now we're allowed to use the integration by partial fractions. So let's see what this looks like. So what we're going to do after that is we factor q of x, which is our denominator, into linear and irreducible quadratic factors. What I mean by that, a linear factor is something that looks like ax plus b, right? So x minus 1 is an example of a linear factor. And we want this to be where a and b don't have any common factors, right? So I don't want something like 2x plus 4. This isn't good because I can still factor a 2 out of that. Okay. And then what I mean by irreducible quadratic factors is that we have something that looks like ax squared plus bx plus c, where b squared minus 4ac is less than 0. What this means is that if you have something like this, and you try to use the quadratic formula on it, you're not going to be able to get real numbers, because this being true means that your square root will be negative. right? So remember the quadratic formula, negative b plus or minus the square root b squared minus 4ac all over 2a, right? That's my beautiful singing voice. So if this part right here is less than 0, then you're trying to take the square root of something that's negative, and this just isn't going to work. So this is what I mean by irreducible. All right. Then after that, we're going to express this proper rational function. What I mean by a proper rational function is that the degree on top is less than the degree on bottom. We're going to express it as a sum of partial fractions that look either something like this or something like this. What this is saying is that when we have a linear factor on bottom, we just put one constant up on top. When we have a quadratic factor on the bottom, we're going to have a constant times x plus another constant. This probably isn't making too much sense right now, but hopefully it will once we start doing some examples. So let's look at case 1. Case 1 is going to be where our denominator is nothing but the product of distinct linear factors. What I mean by that is that our denominator isn't something like x plus 1 squared. Keep in mind, this is a product of linear factors. Just because we see a 2 here doesn't mean this is a quadratic. What this would be is this would be x plus 1 times x plus 1. This does not fall in case 1 because these are not distinct. They're the same as each other. So let's look at this first example. Well, let's first notice that I could rewrite this as the integral of 4x minus 1 over, if I factor the bottom, we'll get x plus 2, x minus 1. And if your factoring skills are just like long gone because you haven't used them in a while and you've kind of forgotten how to do this quickly, feel free to reach out to me and we'll get you right back up to speed. Okay, don't be afraid to mention that or anything. And so now what I want to do is I want to use our method of partial fractions. So whenever we have linear factors on the bottom, we just put some constant on top. So let me show you what I mean by that. What we're going to do is we're going to write that, we're going to write that this fraction that we have right here, 4x minus 1 over x plus 2 times x minus 1, this can really be expressed as a over x plus 2. Right, I'm taking one of my linear factors and just putting a constant over the top of it, and I'm choosing to call that constant a, plus some other constant, b, over x minus 1. Now what I'm going to do is I'm going to multiply by the denominator on both sides. When I multiply by the denominator on the left-hand side, that'll just cancel it out, so we'll get 4x minus 1 down here is equal to, now, notice that when I multiply by the denominator on the right-hand side, we end up with, we'd have a times x plus 2, x minus 1, over x plus 2. And so what would happen is these x plus 2's would cancel. And we just have a times x minus 1. So I'm going to have a times x minus 1 plus b. Similarly, when I multiply by the denominator over here, the x minus 1's will cancel and we'll just be left with b times x plus 2. And so this tells me that 4x minus 1 is equal to, now I'm going to show you two different ways of doing this. Okay. One way, let me stop right here. So one way is that we just plug in stuff that makes these equal to 0. Alright, so if I do x equals 1, so I'm going to plug in 1 on the left-hand side. That would give me 4 minus 1, which is 3. is equal to, so we'll have a times 0, so that's 0, plus b times x plus 2, which is 3. And so then that tells me that in order for this to be true, b must be equal to 1. Now, to get the other value, what I'm going to do is I'm going to plug in x equals -2, because that'll make this part equal to 0. When I plug in x equals -2, this will give us, on the left-hand side, -2 times 4 is -8, minus 1 is -9. So -9 is equal to a times -2 minus 1, so a times -3, which means that 3 is equal to a. And so now we've got our a and b values. That's one way of doing this. It's probably my favorite way, except for the fact that it's not always guaranteed to give you all of your constant values. So go ahead and take note of that. But then our other way of doing this, and this is the way I'm going to use throughout this entire set of lecture notes, you're free to use the other way to kind of knock out some of the constants sometimes. But I want to stick to the second method because it's always going to work for you. So what I do is I distribute everything on the right-hand side. So we'd get ax minus a plus bx plus 2b. Now what I'm going to do is I'm going to group everything on the right-hand side. So everything that has an x attached to it, I'm going to group that together. So I'd get x times a plus b. What I've done is I've taken these two, we're adding them together and factoring out that x. And then for just our constants, we'll have -a plus 2b. Now what I'm going to do is I'm going to notice that these sides have to be equal, which means that the coefficient of x on this side has to be equal to the coefficient of x on this side. So we'll get a plus b equals 4, which means that a is equal to 4 minus b. And then on the other side, so the other thing that we have is that this is a constant right here, and so it must be equal to this constant right here. So -a plus 2b must be equal to -1. Now what I'm going to do is I'm going to substitute this in for this a right here. So that'll give me -4 minus b plus 2b is equal to -1. Okay, so applying this negative, we'll get -4 plus b plus 2b is equal to -1. So this will give us, adding 4 over to the other side, we'll get 3. b plus 2b will give us 3b. So b must be equal to 1. Alright, now plugging this in for b over here, we'll get a equals 4 minus 1, which is 3. Alright, so I'm going to circle these. It's always important to keep this in mind. Alright, now we can rewrite our integral, right, because we know that this has to be true. And so what I'm going to do is I'm going to use this side of our equation to replace this right here. And I'm just going to substitute our a and b values. So this becomes the integral of a over x plus 2. So that's 3 over x plus 2 plus b over x minus 1. So 1 over x minus 1 dx. Right? And so that should be something that we can break up into separate integrals, right? Here's one integral, here's another integral, factor out our constants, and then integrate using u sub to get that this is something like 3 ln absolute value x plus 2 plus ln absolute value x minus 1. Whoops, it's not a parenthesis. and then plus c. Okay, so that's one I'll solve out, but a lot of our integrals work pretty much the same. We get the same type of rules here. And for ones where there's something tricky going on, I'll go ahead and mention it, and we'll look at that part. Now for our next problem, we're going to start looking at case 2, which is where our denominator is still going to be a product of linear factors, but they're not going to be distinct. They're going to have repeated linear factors. So a good example is this one right here, where, so what we do, oops, sorry, wrong color. What we're going to do is we'll rewrite our fraction. So we've got x cubed times x plus 1 squared is equal to, now I'm going to look at our two different linear factors. One of them is just x, the other one is x plus 1. And so what I do, x is being raised to the power of 3. So we'll have a over x plus, so now I've done x, now I need to do x squared. So we'll have b over x squared. And then we have to do x cubed, c over x cubed. So you have to do 1 for each of the parts of that linear factor, if that makes sense. Right, and so similarly, when we have x plus 1 squared, we should have d over x plus 1 plus e over x plus 1 squared. I'm going to go ahead and move this down just ever so slightly, just to save room for when we write our integral later. And for some reason that didn't move. Okay. Now, what we need to do is we need to do the same thing we did on the last problem where we multiply both sides by the denominator. When I do that, I'll get 1 equals, okay, so if I multiply this right here with x cubed over x plus 1 squared, I'll cancel out with one of the x's and I'll be left with ax squared times x plus 1 squared. Then we'll have bx x plus 1 squared plus c times x plus 1 squared. Plus, now we'll be canceling out one of the x plus 1, so I'll have dx cubed times x plus 1 squared, times x plus 1, plus e times x cubed. Okay, so this is one of the cases where we can knock out one of our constants pretty quick by just plugging in x equals negative 1. If I plug in x equals negative 1, this goes to 0, this goes to 0, this, and this. And so we'll just be left with ex cubed. So I'm going to do that. I'm going to start combining our two methods. So I'll write it down. If x equals negative 1, well, there's no x on the left-hand side, so that just stays as 1. And then we'd have e times x cubed, so that's negative 1 cubed, which would just be negative 1. And so then this tells me that e is equal to negative 1. Alright, now let's see where I can move from there. If I plugged in x equals 0, okay, so if x equals 0, then we would get, this would be 0, this would be 0, this would be 0 plus 1 squared, so it's not going to be 0, it'll be something else. That has an x cubed, so that has to be 0. That has an x cubed, so that has to be 0. So I'll just be left with the c times x plus 1 squared. Okay, so I get 1 equals c times 0 plus 1 squared, so c times 1. Which means that c is equal to 1. Okay, now what I'm going to do is erase this, but we're going to keep in mind e is equal to negative 1 and c is equal to 1. So, in fact, what I'll do is I'll save just this part. That's great. I didn't want the C part anyways. We'll delete this part. Sorry about that. Okay. So we've got C equals 1 and E equals -1. So keep that in mind down here. C equals 1, E equals -1. Now I'm going to show you, so that was our first method, right? How we can get some quick constants. But notice we weren't able to figure out A, B, or D. So what I'm going to do is I'm going to go ahead and FOIL this out. To do that, I'm going to note that x plus 1 squared is equal to x squared plus 2x plus 1. So this is 1 equals, if I multiply this with ax squared, I get ax, sorry, let me write this a little bit closer. Ax to the 4th plus 2ax cubed plus ax squared plus, now I'm going to multiply this with bx, so that'll give me bx cubed plus 2bx squared plus bx. Now I already know that c is equal to 1, but what I want to do is we're going to make some formulas out of this. So let me go ahead and multiply it out. We'll get cx squared plus 2cx plus c plus, now I have dx cubed times x plus 1. So this becomes dx to the 4th plus dx cubed, and then plus ex cubed. So now I'm going to group everything that has an x to the 4th. And so I like to start marking these out. So I've got an ax to the 4th and a dx to the 4th. This is going to help me make sure that we don't forget about anything. Now I'm going to look for my x cubeds. So this will give me 2ax cubed. So 2a plus, then I've got a bx cubed, so I need to add a b. And then there's a dx cubed and an ex cubed, so I need to add a d and an e. Alright, then we're going to look for our x squareds. And so I'll get an ax squared, a 2bx squared, so it's going to be a plus 2b. And then we've got a cx squared. So this becomes plus c. Now I'm going to start looking at the ones that have just x next to them. So I've got a bx and a 2cx. So this is going to be b plus 2c. And then plus c from this plus c right here. And now I'm looking back. I've crossed every single term out with a green line, so that means I've used everything. Alright. Now, what I notice is that I have an x to the 4th right here, but no x to the 4th on the left-hand side. Now, there is technically a x to the 4th on the left-hand side of this equation. It's just being multiplied by 0. So that tells me that a plus d is equal to 0. Same thing with x to the cubed. I don't see an x to the cubed over there. That means it's being multiplied with 0. So this means 2a plus b plus d plus e is equal to 0. Same thing with x squared. We'll have a plus 2b plus c is equal to 0. And then same thing with b plus 2c. And then c, we would know, has to be equal to 1. But we already have that, so it's okay. Well, so since c is equal to 1, I can plug that in right here. And that gives me that b plus 2 is equal to 0. So b must be equal to -2. Alright, now I can plug into this equation. I'll plug in our b and our c value. So I'll get a plus 2 times -2, so that's -4. Plus c, so that's +1 is equal to 0. So this is really a minus 3 is equal to 0, so then a must be equal to 3. Now I can plug all of that into this equation right here, or I can notice the only thing I have left to find is d, so I could just plug into this equation right here, right, because we already found e earlier. So plugging in a equals 3 here, we get 3 plus d is equal to 0, so d must be equal to -3. So here's our constant solutions. So then I can rewrite this integral as the integral of, let's see, so I should have a over x, so that'll be 3 over x, plus b over x squared, so that's -2 over x squared, plus c over x cubed, so that's +1 over x cubed. And then I should have plus d over x plus 1, so it's -3 over x plus 1. And then we should have, where is it? Plus e over x plus 1 squared, so -1 over x plus 1 squared dx. So that's what our integral should look like. Now, good things to notice. This is an ln. This will be a power rule, an ln. And then this is going to be a u sub, where we u sub for u equals x plus 1. Okay, so like I said, once we use the partial fractions method, the integral, we just split it up into a bunch of different parts, and it really becomes something, probably the same difficulty, if not easier, than the stuff that we did in section 5.5. It's just getting to that point, right? We did a lot of algebra work to get there. Now let's look at case 3. In case 3, we're thinking about, okay, well, what if we have actual quadratics in the bottom, meaning we have quadratics that can't be reduced, stuff like this, right? These are irreducible quadratics because we can't factor those and make it simpler. So what I do is kind of the same as what we were doing before. I'm going to write x plus 6 over the denominator, times x squared plus 4. Now what I do is, instead of just having a over x squared plus 1, right, we just do one constant over a linear term, or repeated linear terms. Whenever we have a quadratic, it's got to be a constant times x plus another constant. So this will look like ax plus b over x squared plus 1. Now I have a different irreducible quadratic, so I have to do a constant times x plus another constant. So I'll use cx plus d over x squared plus 4. So that gives me x plus 6 equals, right here I'm multiplying by the denominator on both sides. And so when I multiply by the denominator here, the x squared plus 1 will cancel. So I'll get ax plus b. X squared plus 1 cancels with itself, and so we'll have times x squared plus 4. And then we'll have cx plus d. Fix that. Times x squared plus 1, because our x squared plus 4s would cancel with each other. Alright. Now, the reason I keyed in on that second method earlier, the one where we're not just plugging in an x value, is because of the fact that that becomes a lot less reliable whenever we're looking at something like this, where we can't just make, almost the entire thing equal to 0 except for just one part with one constant. Here we actually need to distribute, so we'll get x plus 6 is equal to, when I FOIL this out, I'll get ax cubed plus 4ax plus bx squared plus 4b plus cx cubed plus cx plus dx squared plus d. Now we'll group everything. So I'll group all my x cubes. So I'm going to get a plus c. Mark those out. So there's my ax cubed, my cx cubed. I don't see any more x cubes. So we'll close this off. And if I make it through this entire lecture without making a single mistake where I forget one of these to cross off, I'm going to be just astounded. Because it always happens. That's why I mark it off with the green so I can go back and double check my work. Now I'm going to group the x squareds. So I have a bx squared and a dx squared. So this is b plus d. Now I look at my ones with just x attached. So this is x. We'll have 4a plus c. I also think this maybe helps y'all see where I'm getting some of these numbers from. And then we'll have 4b plus d. Okay. So no x cubes on the left-hand side. That tells me a plus c is equal to 0. So a must be equal to negative c. No x squareds on the left-hand side, so that means b plus d must be equal to 0. So b is equal to negative d. Then I do have an x on the left-hand side and on the right-hand side. The x on the left-hand side has a coefficient of 1, so the x on the right-hand side must have a coefficient of 1, meaning this is the coefficient right here, so it has to be equal to 1. So we'll have 4a plus c is equal to 1. Well, now I can use our a equals negative c. I'm going to plug it in over here. So this will become 4 times negative c, so negative 4c plus c equals 1. That'll give me negative 3c equals 1. So c equals negative 1/3. And now we can see that we've solved for one of these constants. Pun intended. Alright, so now I'll continue on. We'll be looking at this 4b plus d. It's a constant, so it has to be equal to this constant over here. So we'll have 4b plus d is equal to 6. Alright, so now I can use our b equals negative d. So this will be 4 times negative d, so that gives me negative 4d plus d equals 6. So I should have negative 3d equals 6. So d equals negative 2. Now what I'm going to do is I'm going to use these two to get our a and b values. So notice that a is equal to negative c, so a will be equal to 1/3. B is equal to negative d, so that means b will be equal to 2. Which means we can rewrite our integral as the integral from 0 to 1 of, let's see, this becomes ax plus b. So that's going to be 1/3 x plus 2 over, let's see, over, that should be over x squared plus 1. Plus, we should also have a cx plus d. So that'll be negative 1/3 x minus 2 over x squared plus 4. Now this one I'm just going to walk through a couple steps to understand how we would do this. So this becomes the integral from 0 to 1. I'm going to break these up into two separate integrals. So this is going to become... Actually, first thing I'm going to do is pull out a factor of 1/3 from everything. So 1/3 times... Now let's look at this first integral. You know what? I'm sorry, I keep on going back and forth. I want to make this as simple to see as possible, so I'm not going to pull out that 1/3. You may pull it out whenever you actually calculate the integral. So we'll split this into two parts. This becomes 1/3 x plus 2 over x squared plus 1 dx plus the integral from 0 to 1. We can factor out a -1 here. I don't think that'll be too bad. So that becomes 1/3 plus, 1/3 x plus 2 over x squared plus 4. Now what I'm going to do is I'm going to take these two and break them up into two separate parts using the numerator. So we get the integral from 0 to 1 of 1/3 x over x squared plus 1 dx plus the integral from 0 to 1 of 2 over x squared plus 1 dx minus the integral from 0 to 1 of 1/3 x plus 2, 1/3 x over x squared plus 4 dx plus the integral from 0 to 1 of 2 over x squared plus 4 dx. Okay, now I'm going to take a look at just one of these for now, and that will show you how to do the rest. So for this one and this one, you can do a u substitution where u is equal to the denominator, and then that'll cancel out the x on top, and you'll get a nice ln integral. However, I think that these two are maybe a little bit more tricky. So I'm going to look at those two. I'll call this 1, and this can be 2. For 1, let me use a color to kind of separate all this stuff. Alright. For 1, we're going to be looking at the integral from 0 to 1 of 2 over x squared plus 1 dx. So the first thing I'm going to do is pull that 2 out. Now what I'll do is I'm going to use that formula from the beginning, which said that the integral of x squared plus a squared is equal to 1 over a times arctan of x over a. So this is going to be equal to 1 over a. So if this is a squared, that means that a is equal to 1. So we'll have 2 times the integral from 0 to 1 of... We're integrating now. So I should have 1 over a. This is a squared, so a must be equal to 1. So it's just going to be 1 over 1. Plus arctan of x over a. So plus arctan x over 1, which is just x. And then we evaluate from 0 to 1. And remember that arctan, so if we have, we're going to have 2 times 1 plus arctan 1 minus 1 minus arctan 0. And so remember that arctan of 1 is like saying, okay, tangent of what radian value will give us 1. Well, tangent's equal to 1 when we get the square root 2 over 2 divided by square root 2 over 2. And that happens at pi over 4. So our 1's cancel, and then this becomes pi over 4 minus arctan of 0. So that's saying, where is tangent equal to 0? Well, that's going to be when our radian is 0. So this becomes 2 times pi over 4, which is pi over 2. Right? And then number 2 right here, right? Let me use a different color. Number 2 right here will work very similarly to this. It's just that this will be our a squared, so a is going to be 2. So when we integrate that, it'll look like 1 over a, so 1 over 2, times arctan of x over a. So that'll be x over 2. So what I mean is that the integral of this is going to be 1 over 2 arctan x over 2. And then we've just got to evaluate from 0 to 1, and we'd have that 2 out front. Okay. Now moving on, we're going to look at case 4. So we have to evaluate this integral. This is a case where we have repeated quadratic factors. Since we have repeated irreducible quadratic factors, what we can do is, well, first I need to notice what's on top. And what's on top is something that is of degree 2. Now, it looks like that's going to be a problem, but really the bottom, since this is a x squared plus 1 squared, this would have degree 4. So we're going to be safe here. So I should have 3x squared plus x plus 3 over x squared plus 1 squared is equal to, so for our first irreducible quadratic, we'll have ax plus b. And then just like for our repeated linear factors, we have to repeat this again, but this time it's going to be for x squared plus 1 squared. So now I'm going to multiply the left and right side by our x squared plus 1 squared. So this becomes 3x squared plus x plus 3 is equal to ax plus b times x squared plus 1 plus cx plus d. Now we'll FOIL out, and we should get 3x squared plus x plus 3 is equal to ax cubed plus ax plus bx squared plus b plus cx plus d. Now we'll group on the right hand side. And so that gives me, let's say we just have ax cubed. That's the only thing with an x cubed. Let me mark that off. Now I look at my x squareds. There's just one with x squared. So there's bx squared. Now I look for my x's. Well, there's an ax and a cx. So that'll be a plus b. And then for my constants, we'll just have b plus 1. Or sorry, that's not, and my handwriting's so awful that looked like a 1. That's actually a d, so plus b plus d. Okay. So now I look, right hand side, we have an x cubed. There's no x cubed on the left hand side, so that tells me that a is going to be equal to 0. Then for x squared, we know b has to be equal to 3, right? Because the coefficient on the left-hand side has a 3. The coefficient of x on the left-hand side is 1, so we must have a plus b equals 1. And this is a good time for us to realize that we've made a mistake, or well, that I've made a mistake. We already got A and B, which were 0 and 3, and 0 plus 3 is not equal to 1. So when I look back, and this is why I should have been marking these off, this is AX plus CX. So instead of A plus B, this should have been A plus C. So we'd get A plus C is equal to 1, which means that C equals 1. Then our constant on the left-hand side is 3, so this B plus D needs to be equal to 3, which means that 3 plus D is equal to 3, so D equals 0. So this will become, we'll have AX plus B. Well, A is 0 and B is 3, so this is 3 over x squared plus 1 plus CX plus D. So this should be C is 1 and D is 0, so this is going to be X over x squared plus 1 squared. And so just for how we would do this, for this first part right here, this is going to be using our arctan rule. And then for the second part right here, this should be a u sub of u equals x squared plus 1. Moving on to example 5, we'll have 10x plus 1 over x cubed minus 9x is equal to, okay, so here's what I need to look at. This bottom is not, this has not been simplified. It hasn't been factored as much as we possibly could have. So what I want to do is I want to factor an x out of the bottom. So this is going to be, let's see, x cubed minus 9x. I'm not doing anything to the numerator right now. I'm just working on our denominator. I'll factor an x out. That gives me x squared minus 9. And x squared minus 9 can be written as x plus 3, x minus 3. Alright, so this will be equal to a over x plus b over x plus 3 plus c over x minus 3. Okay, so then I'll multiply left and right hand side by this x cubed minus 9x, or what's easier is to multiply it by this, because we'll be able to see what's going to cancel out. So this will be 10x plus 1 equals ax plus 3, x minus 3. And for shorthand, I'm going to go ahead and write that as x squared minus 9. Then we'll have plus bx times x minus 3 plus cx times x plus 3. Distributing everything out, I'll have ax squared minus 9a plus bx squared minus 3bx plus cx squared plus 3cx. Now grouping, and hopefully not making a mistake this time, we should have x squared times a plus b plus c. So that's my ax squared, bx squared, cx squared. Then I should have x times 3c minus 3b. So that's this part, and then minus 9a. So this is our constant. It has to be equal to 1. So it tells me that negative 9a is equal to 1, which means that a is equal to negative 1/9. Then I'll have a plus b plus c, so it's negative 1/9 plus b plus c is equal to 0, because the coefficient of x squared on the left-hand side would be 0. And then I'll get another equation that says 3c minus 3b is equal to 10, because that's the coefficient of x on the left-hand side. And so the one I think is least terrible to work with is going to be this one right here, but you could work with the one on the left if you wanted to. I'm going to divide both sides by 3. That'll give me c minus b equals 10 over 3. So c equals 10 over 3 plus b. So this gives me negative 1/9 plus b plus c is equal to 10/3 plus b, so plus 10/3 plus b equals 0. Negative 1/9 plus 10/3, that's going to be equal to, let's see, we need 30 minus 1, so it's going to be negative 29 over 9 plus b equals 0. So b is equal to 29 over 9. And I'm making a mistake here because we had a b plus b, so that should have been 2b. Whoops. So this is 2b equals 29 over 9. So b equals 29 over 18. There we go, there's b. Not too shabby. And this should have also been positive 29 over 9, so then this on the right-hand side should be negative 29. Okay, so plenty of mistakes made there. You can kind of start to see how it can be very easy to make little mistakes on these problems. Alright, then I'll plug that in for our c equation. So we'll get c equals 10/3 minus 29 over 18. So it'll be 60 minus 29 gives us 31, so c equals 31 over 18. Alright, so this will make our integral kind of gross, but it'll be okay. So this is going to be the integral of a over x, so it's negative 1/9 over x plus b over x plus 3, so that was negative 29 over 18. Negative 29 over 18 over x plus 3 plus c over x minus 3, so that's 31 over 18 over x minus 3. So this is one of those WebAssign quality problems where you just get, big nasty fractions that can't be simplified. But the nice thing is that we just separate this into 3 parts, pull out that ugly fraction on top, and then just use our ln rule. So the integral from there should be pretty quick. Now, for these last few pages, there's one problem that I'm going to go ahead and work out. And it's actually going to be the shortest of these 3. So you'll have example 6, example 7, and example 8. And I'm going to go ahead and get you started on number 8 as well. Example 6 will be a good place for you to practice long division. I know a lot of y'all were saying you wanted more example problems. So this will be something where I'm going to upload the solutions. That way you'll be able to double check your work. But this is more example problems for you to do where this doesn't count for any points. So there's no risk in doing it. And you get to double check your work, ask me as many questions as you want on it, and really get to just make sure that you understand the material. So for example 6, this is a good long division problem. right? So reason we have to do a long division is because the degree on top is 5, the degree on bottom is 2. Then for example 7, so this is the one I wanted to work out real quick. Just because we see a fraction doesn't always mean it's going to be a partial fraction. For example, if we look at this, we can't factor x squared plus 4x plus 29. So what we would do is we would write 1 over x squared plus 4x plus 29 is equal to ax plus b over x squared plus 4x plus 29. Then we'd multiply by the denominator on both sides, so we'd get 1 equals ax plus b. So then a would have to be equal to 0, and b would have to be equal to 1. Plugging that back in, that's the exact same integral that we started with. So our partial fraction methods does not apply here because it doesn't give us anything different than what we started with. Instead, what we have to do is we have to complete the square on the bottom. What I mean by that is we rewrite this as 1 over, this is x plus 2 squared plus 25. Right, if you need a reminder on how to complete the square, I'm going to call this dx. All right, get my dx in up there. If you need a reminder on how to complete the square, please don't feel scared to reach out to me. It's something that doesn't get used a whole lot, but it can be really handy for problems like these. Just because I just said it doesn't get used a whole lot, that does not mean don't study it. That does not mean you don't need to know it. In fact, it means that you will probably need to know it for the exam and to do homeworks and quizzes and stuff like that. Okay, so then we'll use our arctan rule. And so that tells me that this is going to be equal to 1 over a. Well, this is our a squared. So a must be 5. So this is 1 over 5 times arctan of x over a. So this is going to be our x. X plus 2 is going to be our x. So this is going to be x plus 2 over 5. And then the magnificent plus c. Alright, so that's all of example 7. Pretty short problem. You just need to realize that we're using that arctan integration rule. Now, for this problem right here, what I recommend that you do is that you start by breaking this up into 8x minus 2 over x squared plus x minus 2 dx minus the integral of 7x e to the negative 7x dx. This part on the right here, this should be a good place for you to practice integration by parts. Alright, you can use the table method or you can use the actual formula. Either way works. Then the other thing is for this portion right here, this is where you'll get to practice our partial fractions. Okay. For this, I don't recommend factoring a 2 out of the numerator. It can be really easy for you to make a mistake when you do something like that. If you want to, go ahead, try it with factoring the 2 out, but just notice that you're going to get 2 times the integral of, right, so we've got a quadratic on the bottom, but that can be rewritten as x plus 2 times x minus 1. So you'll have a over x plus 2 plus b over x minus 1. And then you'll split this up into 2 integrals, and you have to just make sure, so we'll have 2 times the integral a over x plus 2 plus the integral b over x minus 1. And so you just have to make sure that at the end you multiply by that 2. So whichever way works best for you. But this is going to go ahead and conclude the end of this lecture. And so I will also post another video You won't have to watch the whole video. I'll announce somewhere in the middle of the video where you can go ahead and stop and have everything covered for Wednesday's activity.